Shear, and I think we're past the time that Pinar should start actually by 3 minutes. So Pinar, I'll pass it to you.
All right. Okay. Well, welcome everyone to our monthly research webinar of Transportation Infrastructure Precast Innovation Center. We have 3 speakers today, but before that, I think you all know me, but my name is Pinar Okumus. I'm an associate professor at University at Buffalo, and my title for the center is the associate director. So we'll have these 3 presentations, each 20 minutes, and we'll follow that with 5 minutes of questions. You can hold on to your questions and ask them, unmute yourselves at the end of the each presentation, or if you cannot hold on to them, you can put them in the chat box and we can read it at the end. Please mute yourselves other than the speaker, and with that, I think there's no other announcements, right, Basim, so we can get started.
Yes, thank
So
you.
our first presentation is from University of Texas at San Antonio, and we have 2 speakers. We have Professor Kai, who's an assistant professor at University of Texas at San Antonio. She holds her PhD degree from Purdue University, another partner at the center, and also MS and BS degrees from Tongji University. She works on innovative sensing, artificial intelligence, and robotic methods, construction automation, infrastructure and building management, and community resilience. And she's received funding from our center, as well as NSF and NIST. We also have Dr. Kai's master's student, Juan Carlos Cruz, as a presenter. And he's working on robot system development and simulation. So with that, I'll hand the floor to them to talk to us about UAV-UGV, gaze-directed UAV-UGV coordination.
Okay, yeah, thank you for the introduction. Can everyone hear me? Okay, great. Then I'll go ahead and share my screen here, and then we'll get started. Okay. Okay, I should be sharing now. Can everybody see that, hear me?
Yes.
Excellent. Let me minimize this. Okay, so my name is Juan Carlos Cruz. I'm a master's student here at UTSA, and I'll be presenting our work on gaze-directed UAV-UGV coordination framework for on-site quality inspection of precast bridge construction. So in these slides, I'll be going over some of our project motivations, as well as related technologies that led to our proposed framework, and then some of our developments thus far. So one of our biggest motivations that we had is for across the supply chain for prefabricated concrete structures and precast members, especially in the offsite fabrication, you have very thorough inspections that are done. So for example, you have component dimensioning that's done after it's fabricated. You have different tensile strengths and material testing that are done, and various lab work that gets completed. And then once the bridge is fully constructed, you have very well documented and thorough regional and national level inspections that are done on these bridges. However, when you get to the actual in-process and on-site construction of them, it can be a little more difficult to get very thorough testing done and inspections. As we see in the picture here, the sites can be very chaotic and dynamic. So it's difficult to get these thorough testing done. And it's for a variety of other reasons, like it's difficult to get sophisticated sensing and testing equipment out there. However, these by doing it manually and having less rigorous inspections out on the site, we miss out on various structural deficiencies and defects that can come along when we get these members, either due through the transport or something was missed during the actual previous inspections. So because of that, and because of innovations in aerial and ground technologies for robots, we're able to get more sophisticated automation equipment out there, so that it's smarter and more capable robots that are enhanced by AI and improved battery capabilities. So these robots offer the potential to augment the inspector's capabilities on site. So that is either working on multiple sites remotely, or doing fully autonomous inspections of certain processes. However, each individual component, so the aerial and ground robots, they tend to have their pros and cons. So by putting them together in a systematic framework, we're able to overcome these individual cons. So I'm going to discuss some of the other approaches that have been done to automate inspection. So in some cases, we've seen works done that can do BIM to real monitoring. So this can monitor different progress of a construction site to make sure structures are aligned and ensure the progress is going as expected. In the actual fabrication steps, you have intelligent robots that can be set up with different scanning equipment in order to check tolerances and see if there are any deviation in the output. And all this is thanks to improved sensing and sensing techniques and technologies that let us get more accurate dimension and geometric dimensioning capabilities. And we also see some specialized robots. So in the bottom right corner there, you have a wall climbing robot that's able to monitor the health of different structures by monitoring the cracks and fractures that happen in these structures. So one of the difficulties of these, though, is that the generalized autonomy, so having a fully autonomous robot is still a very challenging task. So many of these robots are teleoperated. So teleoperation is when you have a human operator interacting with an interface. So a joystick controller or button-based controller, as we see there in the control here. You can also have pose-based control, where a human pose corresponds to a robot action. You also see a lot of work being done with virtual reality headsets. So that is, it still takes advantage of some of the joystick-based control, but it augments the user's perception so they can see things maybe they couldn't see before and see them in a three-dimensional space. And one of the benefits of this virtual reality headsets too is that they allow us to get gaze input. So in human-to-human communication, gaze is really important because it shows us the attention and intention of another party. It works the same in a robot-to-human task. We can use gaze to communicate objects of interest or to directly use gaze to control a robot through different mapping methods, as we see here. So that leads us into our proposed framework. So we broke down our framework into 3 different tasks that involves coordinated navigation between the 2 robots using gaze-enabled and AI-enabled interfaces to improve productivity of the remote operator. And then, as mentioned before, to integrate and test these out in the real world, because that's very important in seeing the limitations of your framework. Now, for our proposed framework, it involves a remote operator. So that means someone who is trained to do the inspection or skilled in with specific domain knowledge of how the inspection is supposed to be conducted, having them work in a remote office space or something like that, and then having the robots actually out in the field. So in our coordinated navigation setup, we have a aerial robot. So that is a drone. The drone, it has very high mobility. However, it lacks payload capabilities and long battery life. Usually the drones can go an hour or 2 on their battery. So that prevents very thorough inspections being done with a drone. So to circumvent that, we use the ground vehicles, and that can be really any ground vehicle. So quadrupeds, bipedal robots. In our case, we use the 4-wheeled robot. So that robot would then go out with a specific payload suite, so different sensors and whatever is required for that inspection, and be able to do a more thorough inspection of the concrete member. So with the UAV, we're able to go out and get contextual data, so that is like image and video data, as well as GPS, and then use that GPS and contextual data to further guide the ground robot, so it's able to get to different areas autonomously. And the way we incorporate gaze into this framework is twofold. So we have it gaze being used for the UAV controller to set waypoints automatically. So as you can see, like in this controller, you still have two joysticks to control the drone. However, to actually set the point, you need another interface method to do that because some of these aren't touchscreen. And then we also use a gaze in the actual ground robot movement control and to gather data points across the inspection when the inspection is ongoing. We'll go to the next slide. Right, so as you can see there, our tasks are a bit out of order. That's because we started with a gaze framework beforehand because we were doing work with gaze prior to this. So for the gaze-based control, the framework we've developed thus far is primarily for the ground robot. So that's taking the gaze through these glasses here. Now these are the pupil core glasses. These have a front-facing camera and then the gaze tracking elements here. So the gaze tracking and the front-facing camera allows us to translate the user's gaze into the world view. So that lets them correspond their gaze to where they're actually looking. And we use that technology to then select objects on the screen. So whenever we have our remote robot out in the field, we're able to stream the video and then select objects of interest from that video to then, so the user can select objects that they're interested in inspecting once the robot actually goes to the site. So once the user selects the object of interest, that object is segmented. So that means it's automatically isolated from the rest of the scene. So if you have like a large construction scene and you have a like very noisy environment, you're able to isolate the object of interest. And then what happens next is we send that object to the robot, and the robot then finds that object in its scene and begins to navigate to it. So this lets us identify remotely what the robot should then be inspecting exactly. And in this case, we use a ClearPath Husky robot, which is what we have on hand in our lab, as well as depth sensing cameras to determine the distance from the object of interest. So we have different, we set up a user interface for this. As you can see, our interface is modular and floating. One of the key points for this is that it would then theoretically allow the remote operator to be able to use the gaze interface across different job sites. So they could have different video streams coming in from the robots on different sites and be able to do inspections across different sites. So for this, we set up a menu bar that is an entry point to the application. We set up a network window that allows the remote connection to the robot. We have an inspection window. Now this shows the perspective of the world view. So the yellow dot you see there is the real-time rendering of the user's gaze. So after they select a target from the scene, the target gets segmented. So it looks like this, and then that gets sent to the robot in this segmentation window. So we conducted a pilot study using this framework to control the ground robot. For the pilot study, we had a remote robot and a remote operator inside our lab space. And we had 3 separate objects of interest to inspect. So we had a cone, a small wood plank there, and a large wood block. So what we found out from this pilot study is, as you can expect, the small wood plank was more difficult for the user to land their gaze on. This was, yeah, it could cause strain to the user for their gaze because they had to keep reattempting that small, precise target matching. And then what we also saw is that through the matching method we used, even if the user lands their gaze on, say, that center cone, if you have various identical looking objects, it can have a false positive example where the robot thinks it should inspect that instead of that. Then after we did that, we opened up the lab space a little bit and reconducted the experiment, but then actually demonstrated the navigation portion of it. So this is sped up, but after the target would match in the center screen there, the robot then does some sort of inspection. In this case, it was just a little circle around the target. Right, and that takes us to the multi-robot navigation portion. So as we said, this framework takes advantage of a drone and a ground vehicle. So with a drone, we're able to cover a large area and different objects of interest in a site. So with our framework, the drone is driven to different objects of interest, different concrete members we want to inspect. And then the GPS point and contextual data is saved on a central server, what we call a base station. And then once all those waypoints are gathered, the ground robot then localizes those and creates a navigation plan so it can cover different areas within the job site. And once the target is found with this framework, it doesn't do an autonomous inspection. In our case, it would request the human inspector, the remote operator, to help complete the inspection. Right, so we tested this outdoors, the first portion of it, which is developing the GPS-based waypoint package. So for this, we set up some waypoints right outside our lab space. So it's not too much of a distance. But yeah, this software package we developed is important because you can't directly translate latitude and longitude into robot movements. So you need some software in between to do that translation. As you can see here, it navigates to the point, and then we use the same point to navigate it back to the starting point. Yeah, and right here is moving autonomously. Right, and then to simulate the mission, sorry, let me go back a little bit. Here at UTSA, it's a little difficult to fly the drones outside. You need certain regulations. So we use a simulation for a lot of our drone work. Here in our simulator, which is, this is a gazebo simulator. We have the drone flying to a target of interest. I'll skip ahead a little bit here. And then it sets a GPS waypoint and gathers the contextual information that we said before. So once you're actually at a GPS location, the ground robot navigates to there. You need to actually identify the object of interest. So in concrete structures, we know they're very similar looking if you're inspecting the same component type. So because of that, you need some way of directly identifying which object the user intended to inspect. So different ways that have been done in the literature include April tags and QR codes. So something like this that are affixed to the concrete members. And you have RFID technology too. These can be actually embedded into the structure during the fabrication stage. Some of the downside of those are that they require additional processing steps across the supply chain. And then for, say, April tags or QR codes, these might not be that durable, or they might affect the appearance of the structure. So our selected approach is to try to see if we can do this visually through different visual matching networks that are being done recently. So we here at UTSA, we have a drone cage that allows us to fly the drone without any additional licensing. So what we do is we have a similarity matching method that takes advantage of a CNN convolutional neural network to get features between two images. So in this case here, oh, sorry, it's low quality. Oops, we go back. Yeah, in this case here, at the top there, we have a image from the aerial perspective, so from a drone. And then the bottom here, we're capturing a video with the ground perspective. And sorry, it's still very low quality, but at the top right corner, you have actual like, sorry about that. You have a real-time rendering of a similarity. So in this case, you can barely see it, but it's 0.44, so 44%. We gauge similarity between two images based on the feature outputs and the matching outputs, as well as a homography calculation. Lets us do calculation between different perspectives. And at the bottom here, we also test this in real time in simulation. The simulation rendering is a little slow because the matching architecture comes out at about 8 to 9 frames per second, which is slower than what you would expect from a camera, so like 15 to 30, but it's still good enough to validate our method along different points. So at the top there, you see the target, and then here is a real-time video. Okay, so then to actually conduct a simulation, and what we plan to do outdoors as well, let me skip ahead here. So the drone, prior to this ground robot simulation, it went to the GPS location, which is around here where my mouse is, if you can see it. And then it captured images of the object of interest, which is here. It's like a crate or something. So the robot, what it then does is it navigates to the GPS point, as we can see it there. So it's doing that autonomously. And then once it gets to that point, it needs to figure out what, from the reference image, which isn't shown in this video, sorry. From the reference image, it's able to gauge similarity between all of its scene. So it conducts a scan, a 360 scan, and then it continues to approach the target until it eventually says the similarity isn't improving anymore. So I'm going to request the human operator. And this is because the GPS, depending on your sensors, they can only get within meters of the specified target. So because of that, we need some additional method to get closer to the actual unique concrete member that we want to inspect. So in this case, it just showed getting to the point, and then it gets it right here, which was the object of interest. Okay, so that takes me to the planned work. So down here, we show the picture of our plan that we're going to do. We're going to conduct the same simulated mission with some waypoints in an urban environment. This is our downtown campus. We're going to drive the robot autonomously using GPS and then the similarity matching method. That's going to be our field testing portion. Once we improve the gaze a little bit more, we're going to use that and integrate it into the completed framework to then test outdoors. And this is the drone cage facility we have here at UTSA. This is probably where we're going to conduct our final testing for this and set up some concrete structures out there. Okay, so I think I'm under 20, but that brings me to my conclusion here. So for our testing thus far, we've seen that the gaze control methods can use some work, and we still need to integrate the drone method, which we're working on right now. It can be difficult to get those precise movements, but one method we have in mind to improve our method on that is to directly translate the gaze into the robot's video feed. We're going to do that by bounding the gaze to the incoming video and then translating it directly to like pixel points on there. And that removes the uncertainty of different feature matching methods. And then for the multi-robot navigation, one thing we want to do too is to create maps from the drone. So by mapping the scene with the drone, we're able to create more accurate navigation plans to more accurately move to the specific member of interest. And in those maps, we'll probably still rely on the GPS points for localization, and possibly testing on some other ground robot platforms to see how they perform with this kind of framework. And then finally, for the object identification, with improved mapping that we plan on doing, we think that might help in actually localizing specific members in a construction site. So that's going to be our next steps. And finally, I'd like to give thanks and our acknowledgement for the funding for this project. And that's my last slide.
Thank you, Juan. All right, any questions?
I would like to ask a question, if I may.
Yes.
So thank you, Juan, for a very nice presentation. I am not in that area, so I found it very interesting that we are actually moving into almost autonomous inspection. If I understand you correctly, the purpose was to be able to have the inspector do more than one inspection, right? Because otherwise, if it was focusing on one, it would use just the the mouse and control the robot. So my question is, assuming that I am the inspector and let's say I'm doing 5 sites or something like that, and I deploy the robotic soldiers to do the inspection, when they finish the inspection, are they automatically stopping themselves, or do I need to go back and check what they're doing? You know, how is the end of this operation working?
Oh, that's a great question. So I guess our focus has been to the inspection. So I'm not sure how it would be done afterwards, but I would imagine it'll have some base station that it'll go to, either for charging or for something similar to that. Yeah, but I don't exactly have an answer for the end point after this. But that is, yeah, something we should consider.
Maybe let me explain this. So this project emphasizes to help the use the robot to help inspector to go to the inspection, which is the data collection phase. And after that, in terms of the robot itself, it can navigate to the base station autonomously, no problem using this method. But what is really important is how to process those robot collected data for inspection, right? So I think that is this is the open and flexible framework that can be integrated with other AI algorithms. For example, now there are a lot of studies using, for example, the cameras or images to detect the concrete cracks, for example. That is a separate module and can be potentially embedded to this program, framework. Because what the robot do is actually navigate to the target, collect sensor data, could be images, could be LiDAR. And in our case, we haven't done the downstream task yet, which means the inspector may need to check those images manually. But with other algorithms, existing algorithm in other studies, they may use the AI algorithms to automatically process those images for inspection.
And the images or data are physically stored on the robot?
That could be streamed to the server of the inspector. So it can be stored and can be processed later, or with some real-time processing algorithm, it can be processed also. But that will be saved.
All right, thank you.
We can take one more question. I have a quick question for you. So I've done some bridge inspections in my youth, and there's usually traffic on the bridge. So, you know, you look left, you look right, you run across and then inspect the other side. So how has that come to play with the robots? Yeah, that's actually a really good question, because here in San Antonio, they're doing construction on the interstate. I guess they're putting up some new bridges here as well. And I've seen the sites that they're working on is very constricted, and it's like right next to traffic. So I think in those cases, it'd be up to the, I guess, the inspection company or whoever's performing the inspection to kind of figure out, is this the best use case for that? But that's also where I think different robot platforms can kind of play, where you have like bipedal robots. So the humanoid robots, if you've seen those recently, that could fit into the framework as a ground robot. Also these quadrupeds. So have you seen the Boston Spot robot, Boston Dynamics Spot robot? Something like that could be a little, could work in those very like rough terrain and very closed terrain environments. But to actually cross traffic, that'd be a little more difficult.
And also that could be the motivation of using robot instead of human to do the actual inspection because of the safety hazard, right? But either way, if we use that to inspect some existing bridge or something under construction with other traffic, we may need to do some traffic control. But the goal is that we want to protect a human worker from those dangerous scenarios.
All right.
Yeah,
Thank
thank
you
you.
very much. Thank you.
Thank you.
And thank you, Dr. Kai. So
Thank you.
we're going to move on to our second presentation. We're going to University of Illinois Urbana-Champaign now. We have a PhD student, Hadil Helaly, to present. She's, like I said, she's a PhD student with architectural background, actually. She holds a master's degree from also University of Illinois. And she has experience in data analytics and machine learning, and she's going to tell us about how she uses that for construction efficiency, performance, and economics today. So that, go ahead, Hadil, if you could share your screen, please, or presentation.
Good afternoon, everyone. Can you hear me?
Yeah.
Let me just share my screen. Just a minute. Yeah, can you see my screen?
Yes.
Great. Let me just go over start from the beginning. Okay. Good afternoon, everyone. My name is Hadil Helaly, and today I'm presenting our work that focuses on optimizing the planning of precast concrete construction, precast concrete bridges to maximize durability, safety, and sustainability. Our research team includes Professor El-Rayes, Dr. Ignacio, Professor Andros, and myself. For today's presentation, I'm going to start with a quick overview, then problem statement, research objectives and tasks. Then I will explain in more details about the first research task, then moving on to the future work, and finally the expected research contributions and impact. As you may know, the US has more than 600,000 bridges nationwide. 42% of those bridges are more than 50 years old. According to the FHWA, 23% of those old bridges are in a poor condition. Additionally, 7.5% of the US bridges are structurally deficient. To address safety hazards caused by these aging and deteriorating bridges, the US federal government enacted the Infrastructure Investment and Job Act that invests over than $300 billion for repairing and replacing the US bridges and roadways. Typically, those bridge projects utilize either conventional cast-in-place construction method, where all the construction activities are performed on-site, or one of the accelerated bridge construction methods that focus mainly on reducing the on-site construction time and traffic disruption, such as precast bridge elements, precast lateral slide, and precast self-propelled modular transporters. In the next few slides, I'm just going to briefly explain each of those construction methods along with their advantages and challenges. Starting by the conventional cast-in-place construction method. As I mentioned, in this method, all construction activities are performed in stage on-site, such as earth moving, formwork, cast-in-place concrete, everything. The main advantages of this construction method, it's low initial construction cost, and also it does not need any or the use of any special equipment such as the heavy lifting equipment, etc. The main challenges, since all the activities are performed on site, it requires a longer construction duration, which lead to extended full or partial lane closure that leads to a significant traffic delays and safety hazard. Moving on to the precast bridge elements construction method. In this method, the major structural components are precast or built off-site, then moved and installed on-site. As expected, this construction method reduces the construction duration and lane closure. Also, it improves the traffic mobility and safety and enhances quality and durability of bridge project. For the main challenges, compared to the conventional cast-in-place construction method, it requires higher upfront cost to order all those precast elements, and also it requires longer planning and design time to plan for all those precast elements, how they will be transported and connected together on site. Third, the precast lateral slide construction method. In this construction method, the new bridge is built laterally in parallel to the old bridge, or in some cases under the old bridge, then moved laterally to its location after it's ready. The advantages, it reduces the construction cost and lane duration to sometimes, in some cases, just few days. And as a result, it improves the traffic mobility and safety. For the main challenges, it requires additional costs for the lateral side equipment and additional space to build the new bridge in parallel or adjacent to the old bridge. Finally, the last construction method is the precast self-propelled modular transporter. And this method focuses mainly on the entire bridge is built offsite, then moved to its location using those SPMTs trailers. The main advantage that it can significantly reduce the lane closure and traffic disruption to just a few hours. So the entire bridge can be installed in just like less than 24 hours, which improve the traffic mobility and safety as well. The main challenges, similar to all ABC construction methods, it's required, compared to the conventional construction method, it's required longer planning and design time, and also it requires a clear travel path to move this new bridge to its new location. The main problem that we're trying to solve in this project, that state DOTs need to optimize the fund they receive for those bridge projects in order to accomplish multiple objectives. And simply those multiple objectives are their strategic goals, including maximizing safety, durability, sustainability, mobility, while minimizing the life cycle cost. To address this problem, we identify the major challenges facing decision makers in bridge construction project. First, during the early design phase, where there are limited project data available at this time, decision makers simply need to decide which construction method they should use in the planned project. And one of the major factors to make their decision is, of course, the cost. So they need to accurately predict the construction cost of alternative bridge construction method in order to identify or determine the most cost-effective bridge construction method. While during the planning phase, after the design is completed, there are several construction decisions that need to be made carefully during this time. Such as the size of precast components, the transportation method, how many trucks there will be used, if they decided to use the SPMTs, what is the optimal size of the SPMTs, also the installation equipment, do they need any special equipment or not? So they need to carefully make or select the optimal option for those construction decisions in order to optimize their impact on the entire bridge and also to achieve their strategic goal, as I mentioned in a few slides earlier. To address this problem, the first objective of this research project focus on assisting decision makers during the early design phase to estimate the construction cost of alternative bridge construction method using the early limited available data during this time. And the best way to do this is to develop the machine learning models that will help them do this. For the second objectives, we need to assist decision makers during the planning phase to find the optimal solution that they can find for all of those construction decisions to achieve their multiple objectives, as I mentioned, including maximizing safety, durability, sustainability, mobility, and of course, the cost. And the best way to do this is to develop a multi-objective optimization model that can take all those construction decisions and provide them with the optimal solution that they can use to achieve all their objectives. Each of those objectives is translated into a research task. So for the first task that focus on developing the machine learning models, this task can be was performed in four main phases. First, collecting available historical data of bridge project utilizing alternative bridge construction method. Then after that, pre-processing or like preparing the collected data to ensure its quality and reliability by identifying first the predicted and predictor variables, then classifying the predictor variables based on their type, then cleaning collected data by excluding outliers, then transforming collected data, and finally splitting the collected data into training and testing data set. The training data set will be used in developing the machine learning models that are capable of estimating the construction cost of alternative bridge construction method during the early design phase. And finally, we need to evaluate and validate the performance of those developed machine learning models using the testing dataset. Since now I explained or covered the general plan, I will go over each of those phases and explain them in more details. Starting by the bridge data collection, the first phase. In this phase, we were able to collect historical bridge projects that were constructed between 1992 and 2024 from 29 different US states. Including Illinois, Utah, Pennsylvania, Colorado, etc. It should be noted that each of those DOTs or sources that we collected have their own or their unique system to store their data, and we have to deal with each one of them individually. An example here for the project that we already collected from the IDOT or the Illinois Department of Transportation. We collected the data from three main sources. First, we have to access the contract detail page to just collect the general information about the project, general description, and total cost of the project and the duration. Then we had to go over the plans document to extract all the data we need for this specific project, including the project length, bridge width, ADT, etc. And finally, we have to confirm that we have everything that we collected, everything was correct by visiting the Bridge Information System website to collect all other data that we need. This phase resulted in collecting a total of 413 bridge projects. 202 of them were performed or were constructed using the conventional cast-in-place project, 168 using the precast bridge elements, 33 lateral slide, and 10 precast SPMTs. And since we have a wide range of construction year and location, we decided to use the RS means, the 2024 RS means, to adjust all the bridge cost data to the 2024 and the national average. Moving on to the second phase, the data processing, pre-processing. First, we identify the predicted and predictor variables for our machine learning models. Based on the literature review, we identify the predicted variables as the unit cost of the bridge cost, and that's simply because we can get the total cost of a bridge by just multiplying the unit cost by the bridge length and width. Also, we identify 11 different predictor variables that has a significant impact on the construction cost of bridge project during the early design phase, as you can see, including the project length, bridge length, etc. After that, we categorize the predictor variables based on their type to numerical and categorical. Of course, the numerical has all the variables that have a measurable quantity, such as the bridge length and width. And for the categorical variables, include all the other variables that can have one of several possible values. For example, here, the location type can be either urban or rural. So this is a categorical variable. Third, collected variables was cleaned to exclude all outliers to improve the machine learning model's performance. And to identify those outliers, we develop histograms for all numerical variables to just illustrate the distribution of each of those variables in the collected data set. As you can see here, the majority of the collected bridge project have a bridge length less than 1,500 feet and a bridge width less than 150 feet. This step resulted on excluding 16 bridge projects from the collected dataset that we just mentioned. 3 of them were performed using the conventional cast-in-place, 11 precast bridge elements, and 2 of them lateral slide project. After that, we decided to use a very widely method that can improve the performance of the machine learning models, which is transforming the predictor variables. We use 2 different methods. One for the numerical variables, we use the mini-max normalization method for all the numerical variables, and the one-hot encoding methods for all categorical variables. And finally, we split the transformed data into training and testing dataset, 80% for the training and 20% for the testing dataset. The training dataset will be used mainly for developing or training the machine learning model, while the testing dataset will be used to evaluate and validate their performance using this testing dataset that was never used or seen before by the developed model. And to make sure that we're maintaining those 80% and 20%, not only in the entire data, but in each bridge construction method, we use the stratified test, train, test, split method. So as you can see here, we have in total 157 precast bridge elements. 80% of them will be in the training dataset, 126 bridge project, while 31 bridge project, or 20% of those total prefabricated bridge element, will be in the testing dataset. By that, our data is ready for the model development. So now we're going to move on the third phase, which is the model development. In this phase, we selected 6 different machine learning algorithms that are widely used in a similar problem that can accurately estimate the construction cost of alternative bridge construction method. 3 of them were considered as a linear regression algorithm, or in other words, a simple machine learning algorithm, including the ordinary least square, lasso, and ridge regression. While the other 3 considered as a non-linear regression algorithm or advanced machine learning algorithm that need that we decided to explore it to see if they give us a better performance. Those non-linear regression algorithms, including the random forest, gradient boosting, and extreme gradient boosting. And as I mentioned before, we're going to use the training dataset, the 80% of the dataset, to develop or train those developed model. After that, we need to evaluate the performance and validate the performance of the developed machine learning models. And to do this, as I mentioned, we're going to use the testing dataset that was never used or seen before by the developed model. And we're going to compare their predicted variable to their true variables for each developed machine learning models. Here in the x-axis, you can see the total of 80 bridge project in the testing dataset. And for each point, we're going to find 2 different points. One, the orange one is for the true values, and the other line is for the predicted variables using one of the machine learning models. The first one for the ordinary least square. And as you can see, there is a huge difference between the actual and predicted, while the other one is comparing the actual to the predicted cost that was developed using the XGBoost. To calculate the error for each of those machine learning models, we decided to use 4 different metrics to calculate this error, including the mean absolute percentage error, mean absolute error, median absolute error, and root mean absolute square error. As you can see, all of those metrics are calculating the error, but in a different way. All of them are widely used, and we decided to calculate those 4 metrics to all 6 different developed machine learning models and compare between them to find the best performing model. And here is the result of the 4 main metrics for each developed machine learning models. As you can see here, in general, the non-linear regression models perform better than the linear regression model. That's in general. And if we dig deeper into each of those metrics, we're going to find that the XGBoost provide the lowest MAP of 13.9%. It's outperform all other machine learning models, and also it provides the lowest mean absolute error of $65.2 per square foot and $29.9 per square foot for the median absolute error, while the gradient boosting provides the lowest root mean square error of $113 per square foot. Let's conclude our work in the first task of this research project, and we decided that the XGBoost is the best performing model among all of the developed model because it's outperformed all the other models in 3 different metrics, as I mentioned. Moving on to the second task, that focus on developing multi-objective optimization model to optimize the impact of construction decision on bridge project during the planning phase. This task still in progress, but I'm gonna explain the general plan of this one. Again, this task will be performed in 4 different phases. First, identify all decision variables that has an impact on the bridge project. Next, formulate the optimization objectives and constraint. And as we mentioned, we need to maximize safety, durability, mobility, sustainability while minimizing the total life cycle cost. Then implement the optimization model. And finally, analyze a real-life case study to illustrate the use of the developed model. That gives us, and as I mentioned, all of those steps are still in progress. Let's move us to the expected research contribution. As I mentioned, this research is expected to develop machine learning models to assist decision makers to accurately estimate the construction cost of alternative bridge construction method during the early design phase. And also, we will develop a multi-objective optimization model to optimize the impact of construction decision on bridge project during the planning phase to achieve multiple objectives, including safety, durability, sustainability, and minimizing life cycle cost. This research is expected to have a significant impact on improving the accuracy of predicting the construction cost of bridge project utilizing alternative bridge construction method based on the early design based on the early design data available. Also maximizing the safety of traveling public and construction workers in and around the construction or the work zone, and maximizing the project durability and sustainability as well, while maximizing the traffic mobility during the bridge construction project, and finally minimizing the total cost of the bridges, including the off-site prefabricated costs, shipping costs, and on-site construction cost. The result of this work it resulted on like 3 different publications. We already submitted, or there are 2 already papers are under review. One of them we submitted to the Canadian Journal of Civil Engineering, and the other one to the ASCCE Journal of Construction Engineering and Management, while we are still working on the 3rd publication or third papers. By that, thank you so much, and I'm ready to answer any question.
Thank you, Hadil.
So much.
Sorry, you can't give the a round of applause is what you would normally give, but maybe not on a webinar. Any questions for Hadil?
I have a question.
Yes,
On the slide that she has shown on histogram.
yeah. Yep. This one.
Yes, I could not get, you got nice data and represented the general behavior of different frequencies of the different products. My question, where did you use this information later on? Did you develop any kind of model prediction for this type of histogram?
Can you repeat the question, Professor? Why did I?
Yeah, where did you use this data later on? You collected the data, am I right?
Yeah, I collected the data, yeah.
So where you gained some knowledge, where did you apply that knowledge in the subsequent study?
What was the purpose, in other words, Hadil, what was the purpose of these histograms? What did you do with these histograms?
So these histograms to illustrate the distribution of the collected data, Professor.
And what did you do with it? The outcome of the analysis? What did it affect? How did it affect the development of the models?
Okay, so first of all, we started to develop the model without excluding anything, and we get not like very good result. So we decided to dig deeper how to improve the performance of the developed machine learning models. And one of the methods is to exclude outlier to remove the noise that can resulted by those outliers. And when we developed those histograms, we found that the majority of the project are like like, for example, here for the bridge length, the majority of the project are less than 1,500 feet. That means that those are outliers. and they will have a bad impact on the developed model. That's why we decided to exclude them.
Yeah, but for that you don't need any distribution or histogram. You could just find out the maximum value, then you can find out the outlier point. You don't need to distribute it. My question is there any place where you use this distribution? Most likely it is a Poisson distribution of the data. So did you use that information for any kind of work subsequently?
No,
The short answer is no. The short answer is no.
no, yeah.
We use the analysis, the frequency histogram analysis, just to identify outliers. It could be identified using other methods, but
Yes.
it's simply for identifying outliers and excluding them.
Okay. Okay, thank you.
Can I have one or two questions? All right, I'll ask a quick question while people are thinking. So I'm assuming, I don't know much about the topic other than machine learning, but I'm assuming costs in California would be a lot higher than costs in, let's say, Illinois. So how do you account for that variability?
Yep, exactly. That's why we use the RS means, as I mentioned here. Let me get. Yes, that's why we use the 2024 RS means to account for the variation of the construction years and location. So all the data that we collect from different states will account for a different, are now considered for the national average and the 2024 cost.
Ah, I see. So you're converting.
Yep, yeah.
Thank you. Any other questions for Hadil? All right, thank you very much. So we'll move on to our third and last speaker. So for our third presentation, we have a PhD student from University at Buffalo. Mohamed Hassan Lasheen will be the presenter. He is a PhD student now, but he has received his master's and bachelor's degrees from Cairo University in Egypt. And he's been working on shear of concrete and machine learning since then. So with that, Mohamed, the floor is yours. You can share your screen.
Hello, everyone. Could you see my screen?
Yes.
Hello, everyone. This is my presentation with title Data-Driven Interpretation of Shear Crack for Prestressed Concrete Beams. My name is Mohamed Hassan Lasheen. My supervisor is Professor Okumus and Professor Khorasani. We will start with our research problem. We have a lot of concrete members that have shear cracks due to overloading and they need to be evaluated for its safety. So as an overview for the existing evaluation method, first we could perform load testing. However, it is expensive, or we could perform a finite element analysis. However, it is time consuming and it requires expertise. Or we could use the design code equation. However, it is conservative. So our solution is to develop a tool using machine learning, which make a relation between the crack width and its corresponding load history. As it is shown in the figure on the right, this is our final product. This product is a user-friendly interface, which you take as an input the beam size, reinforcement detail, and the measured crack width from site investigation. And the final output is the shear strength for this member and the loading history. So our output is to determine the shear strength, which is the highest point in this curve, and to determine the load corresponding to the measured crack width from the site investigation. By knowing these two values, we could determine how far or how critical our bridge is by knowing the loading ratio. Then our scope is to help the field engineer to evaluate the cracked member. The field engineer go to site and measure the crack width and collect all information about the cracked member. Then our turn at UB is to predict the shear strength by collecting shear test data and train machine learning algorithm to predict the shear strength. And this step was discussed in detail in TRANS-IPIC in-person workshop. Then the second step, which is our focus at this webinar, is to predict the shear load history by collecting the shear data with crack width record and train machine learning algorithm to predict the load history. By knowing the shear load history and the shear strength, we could determine the shear load to strength ratio. This ratio would help the inspector to determine which bridge is most critical. Then could the crack width be used as a sole predictor, as it is shown in this figure? This figure shows a relation between the crack width on the horizontal axis and the load history ratio on the y-axis. As it is shown, there is a trend that could fit this data, as it is as the red trend. Then there is a multiple trend that could fit this data, so there is a high dispersion. At a given crack width, let's say at 0.02 crack width, the loading ratio could be 40% or could be 85%. So the crack width could not be used as a sole predictor. We need additional feature to be added to our model so that our prediction for the loading ratio could be more accurate. We have chosen this predictive feature, which are beam size, the material properties, pre-stressing and reinforcement detail. Then we have to define the predictive feature which are used to train the machine learning algorithm. So using the parameter in the table on the right, we have constructed 10 predictive features. The first 9 are used to train the shear strength, are used as a shear strength predictive feature, and the whole predictive features are used to train the load history predictive feature. It should be noted that all these parameters are chosen to be easily extracted from the site investigation or from the structure drawing. Then we have chosen 3 machine learning algorithms. These machine learning algorithms are the linear regression, support vector, and the Gaussian process. It should be noted that we have chosen this algorithm because it does not require a large data set to be trained and does not require high computational power for training. As a review from the previous TRANS-IPIC in-person workshop, the linear regression error was 34% to predict the shear strength. Support vector have shear strength error 19% and 14% for the Gaussian process. As it is shown that the Gaussian process gives the least error, so our focus at today's webinar is using the Gaussian process because it is the algorithm which has the least error. Then we start with collecting of data and the filter of this data. So we start with Nakamura at 2013 data set. Then we make additional filtering by excluding deep beam, continuous beam, external pre-stressing, and a lightweight concrete sample. Then we complement our filter data with the sample between 2013 and 2024. So our final data was 897 tests. It should be noted that only 10 beam were complemented to the filter data because most of the research at this period focus on the effect of unconventional material such as fiber, synthetic fiber or steel fiber. Then we go for a visualization of the used parameter. We use the box plot. The box plot is a way of visualization of the value of this parameter. So Q1, which represents this limit, is the 25 percentile value, and Q3 represents 75 percentile value, and the red line represents the median. IQC, it is the difference between Q3 and Q1, and any value at this zone is considered as a well-represented value by this parameter. This black limit is Q1 minus IQR, and this limit also is Q3 plus IQR. Any data outside this zone is considered as outlier and represented by the red cross. It should be noted that the minimum value for the reinforcement, the shear reinforcement and longitudinal reinforcement ratio is 0, because our data set include both sample which has shear reinforcement and does not have shear reinforcement, and sample which has longitudinal and does not have longitudinal reinforcement. Then we go for collecting and filtering of the data for load history prediction. So we use the final shear strength data, and we make additional filtering by excluding any beam without crack width record. So finally, we have 79 tests with 391 crack width measurement. It should be noted that each test could have multiple crack width record. Then we go for a visualization of the load history data set. It should be noted that here there is an additional feature, which is the crack width. Then while we are training our model, we have performed a 10-fold cross validation. 10-fold cross validation is splitting the data set into two sets, validation set and training set. So at the beginning, we split our data set into 10 partition, 9 partition as a training and 1 partition for validation, and we calculate the error for the validation set. We repeat the same process multiple times. We repeat this step 10 times, then finally we calculate the average of this error value to be the 10-fold error. Then to evaluate our model, we need to compare with the existing code. We have it chosen two codes. The first is the H2 code and second one is the ACI. So this plot on the horizontal axis could you hear me?
Yes.
Yes, you froze for a moment, but we're good now. Go ahead.
Just 1 second.
Can you hear us, Mohamed? Oh, we lost him. Oh, no, you're here. Okay, we lost your screen, so you have to reshare. Okay, coming back up. Okay, we can see your screen again.
Okay, so to evaluate our model, we are comparing our result to the H2 code and the ACI in the next slide. So this plot on the horizontal axis is predicted shear strength by machine learning, and on the vertical axis is the experimental shear strength. The red line represents the 45-degree line, or the zero error line. So the error for machine learning was 14%, and the mean ratio between the experimental shear strength and the predicted shear strength by machine learning was 1.01 versus 1.63 for the H2 code. It should be noted that most of the prediction for the H2 code was above this red line. So this means that these predictions are conservative, because the purpose of the code is to design. However, our purpose is to have accurate prediction to be used for evaluation of the cracked member. Then we repeat the same process, but for the ACI, the error for machine learning was 1.01 versus 1.31 for the ACI. Also, most of the ACI predictions are conservative for the same reason. Then to evaluate the machine learning prediction for load history. This plot is drawn. On the horizontal axis is the predicted load history by machine learning, and on the vertical axis is the predicted load history, is the experimental load history. The error was, the mean ratio was 99%, and the error was 10%. It should be noted that there is no current evaluation method for predicting the load history for pre-stress concrete member. So there is nothing to compare with. Then we would like to demonstrate our model using unseen beams. So at the beginning, we have excluded 4 beams out of the training sample to be used for final validation of our machine learning algorithm. We have chosen this beam to include shear reinforcement and to have 0 shear reinforcement. So we have chosen 4 beam. Two beam have shear reinforcement. One of them is poorly represented by the data, and the other one is well represented by the data. The other 2 have shear reinforcement exceeding the minimum shear. So
We lost your screen. You stopped sharing your screen.
okay. Could you see the screen again?
Nope, not yet. Yeah, it's coming now.
Yep.
Go ahead.
Okay. So this is our result for the first beam. The error was I'm sorry for this technical problem. Could you see the screen?
Yeah, yes. Mm-hmm.
So this is the result for the first beam, which has shear reinforcement less than the minimum shear, and it is poorly represented. This is the result for the second beam. It should be noted that the shear strength error was 7% for the well represented, and it is less error than the poorly represented sample as it is expected. For the third beam, which has shear reinforcement greater than the minimum shear, the error was 10%. For the fourth sample, which is well represented and has shear reinforcement greater than the minimum shear, the error was 3%. For the load history prediction, the error was 35% for the first sample, which has shear reinforcement less than the minimum shear, and 15% for the second sample. It should be noted here that we have only 11 samples have shear reinforcement less than the minimum shear, so there is no poorly or well represented beam. For the second data set, which has shear reinforcement greater than the minimum shear, the error was 16% for the poorly represented specimen and 3% for the well represented specimen. Here we are plotting a relation between the crack width on the horizontal axis and the loading ratio on the y-axis. The red line represents the experimental result, and the blue one represents the machine learning shear strength, shear load history prediction. For the first sample, the error was 35%. For the second sample, the error was 15%. For the third sample, the error was 16%. And for the last sample, the error was 3%. It should be noted that our data set include different shapes, so our machine learning algorithm is suitable for different shapes. For the conclusion, machine learning prediction error was 14% for the shear strength and 10% for the load history. Machine learning predict the shear strength with a smallest mean ratio 1.01 versus 1.63 for the H2 and 1.31 for the ACI. It should be noted that the code are intentionally conservative for design purpose. However, machine learning purpose is evaluation, so we need accurate prediction. Machine learning prediction was good when we have a well-represented sample having shear reinforcement greater than the minimum shear. So any additional data of higher quality would improve machine learning prediction. This is our final product, which is a web interface. I will play a video to show a demo for using this web application. This is a cracked member. As an input, we put as an input the beam size, material properties, pre-stressing, and reinforcement detail. And finally, we insert the crack width and press calculate to determine the first value is the shear strength, the second one is the shear load history, and the third value is the loading ratio. So by determining the loading ratio for different bridges, we could determine which one is the most critical. We would like to acknowledge TRANS-IPIC, DOT, and Institute of Bridge Engineering for their financial support, and the other collaborator, Dr. Varan Shandula, Dr. Rodrigo Castello, and Ishika Raj. This is our references. Thank you, and any questions?
Thank you, Mohamed. Any questions for Mohamed?
I have a question on that percentage on the last slide you are showing.
Okay. You mean the web interface or?
Right before that.
Okay.
There is a 10% and 14% this here.
Okay.
If this error is that much, is it acceptable in engineering design?
The 10%?
Yeah, 10%. I'm not sure. I'm just asking.
I think this 10% is good and acceptable, because if we are comparing it to the design code, the error is 30% and 40%. So the machine learning prediction is the least error compared to the available evaluation method.
But civil engineering project involve human, materials, structures. So if the failure rate is that much, failure rate means the error is that much deviated from zero, then how good it is, I have a concern. So I'm not expert in that. I'm just asking from my curiosity.
I think this value is good and acceptable compared to the other evaluation method.
Maybe just to give a benchmark comparison, like if I tested two beams under shear exactly the same in theory, you could potentially get 10% difference in between the two, just because it's shear and it's very unpredictable. So there's that inherent uncertainty, which also impacts our data. So that's why we think 10%, 14% is within that expected variability.
Okay.
Perhaps a quick follow-up to that. This is for mainly evaluation rather than design purposes, because the design code technically has the safety factors, has the reliability built in, whereas here the purpose or objective is for evaluation, which eventually this can lead to, if you have a series of bridges, then you can use this as to understand which ones have priority or the other ones for, depending on its condition, for repair or doing something about it.
Any other questions for Mohamed?
Mohamed, good presentation. Really congratulations, the great work. Great, progress since we met at the workshop. Very small questions I have. first of all, what method did you use in the AASHTO? When you say AASHTO, there are a few methods suggested by AASHTO for calculating the shear capacity. For example, you use the modified compression field
Yeah,
or
yeah,
what?
yeah, Professor.
Modified, okay. Have you tried other methods too, where with different levels of accuracy?
I have compared also with the ACI detailed and simplified approach.
Okay.
So machine learning has the least error on the existing code equation. Yeah,
Okay.
either H2 and the ACI.
Very good, very good. Now, in your calculation, like I like very much the web interface program that you developed. Did you develop this yourself, or how did do you have the skills of developing something like this? That's great. I love it.
It was the first time to work on this area, but there is Ishi Karaj. She was an undergraduate student.
Okay.
She helped me at developing this web interface. Yeah.
Can you comment on, and maybe you already took this into account, the effect of the bridge deck on the results?
Can I comment on what?
If you take the composite action or the bridge deck along with the cross sections that you showed, how would this affect your results? Or maybe you have already taken it into account.
You are speaking about the information which I have inserted to this web application?
The bridge deck, the cross section that you have, did you consider the composite action between, let's say, a precast girder and the deck?
Yeah, there is a sample. Yeah, yeah. While I'm training the model, there is a sample for composite section. So the depth is considering this composite action. Yeah.
Some
Okay.
samples have decks, some samples don't in the training data set.
Yeah. But the definition of depth, from the extreme compression, including the composite or the deck to the centroid of pre-stressing. Yeah.
And that is reflected in this web interface software, right?
Yeah, Professor.
Okay, very good. Yeah, that's all. Thank you.
Any questions for any of our presenters before we conclude today's webinar? All right, I would like to thank all the presenters for their work, for presenting, and also for everyone for attending. So this concludes our webinar. Thank you.
Thank you. Bye.
Thanks, bye.
Bye.
Thanks, everyone. Bye.
Bye-bye.
Thank you. Bye-bye.
Thanks so much.